1947 changed the modern world. At Bell Labs in New Jersey, the transistor replaced bulky vacuum tubes and opened the way to smaller, cheaper, more reliable electronics. Then in the late 1950s and 1960s, integrated circuits put many components on a single chip. That is how modern computing began. Today, chips sit inside phones, cars, factory robots, data centers, satellites, drones, and missiles. They power AI, telecom networks, cloud services, and industrial machines. But the system that makes them is not spread evenly. The United States leads in chip design, chip IP, and EDA software. Taiwan leads in advanced foundry manufacturing. The Netherlands matters because ASML builds the most advanced lithography tools. South Korea dominates memory. Japan supplies crucial materials and industrial inputs. So this is not just a story about technology, it is a map of concentrated control. A small number of countries and firms shape what the rest of the world can build. Hsinchu and Veldhoven sit half a world apart. Yet, if either one stumbles, the shock does not stay in tech. Think back to the 2020 to 2022 chip shortage. Automakers cut production, prices rose, and plants idled because missing chips held up entire vehicles. Now, scale that problem up to the most advanced chips used in AI servers, telecom gear, and military electronics. Taiwan is the clearest single bottleneck in the system, and Veldhoven matters because Dutch export licenses can decide where ASML's most advanced tools go. One is a factory hub, the other is a gatekeeper. Then add geography. The Taiwan Strait is already one of the world's most dangerous flashpoints. A blockade, cyber attack, or prolonged crisis there would not just delay gadgets, it could hit cloud expansion, weapons maintenance, industrial automation, and national planning at the same time. That is why this story starts with two places on a map, not one company alone. In the 1980s, making top chips became so expensive and so complex that the old models started to crack. One company could still try to design, build, package, and sell everything itself, but doing all of it well was getting harder. So the industry split. Fabless firms focused on design. Foundries focused on manufacturing. It looked efficient, and for years it was. Costs fell, specialization improved, production crossed borders. There was a catch. As the model spread, capacity did not spread evenly with it. More and more of the hardest manufacturing work clustered in Taiwan. That trade-off matters because a factory is not just a building. It is yields, trained workers, supplier networks, water systems, power stability, and years of process learning. You cannot copy that overnight by pouring concrete somewhere else. So before we talk about crisis, we have to understand the system that made crisis so dangerous. A global supply chain built to be fast, not safe. In 1985, Morris Chang left Texas Instruments after a long career in the US chip industry. He was 54, and he believed he had been passed over. Taiwan offered him something different, the chance to build. Working with officials and institutions such as ITRI, Chang helped launch TSMC in Hsinchu. The idea was unusual for its time. TSMC would not compete as a branded chip company. It would be a pure-play foundry, making chips for other firms. That sounds normal now. Back then, it was a gamble. For the model to work, customers had to trust TSMC with their most valuable designs. They had to believe a factory in Taiwan could protect trade secrets, deliver high yields, and keep improving year after year. Chang was not just building production lines, he was building confidence in a new industrial deal. You design the chip, we manufacture it. That bargain helped redraw the map of global electronics. Once TSMC's model worked, the rest of the chain split into its own pressure points. Taiwan became central for advanced logic, the chips that do the main computing work. South Korea, especially Samsung and SK Hynix, became dominant in memory, including HBM, the high-bandwidth memory that advanced AI systems need. The United States stayed upstream through EDA software from firms like Synopsys and Cadence, plus major chip IP. Japan remained vital in photoresists, wafers, ultra-pure chemicals, and other hard-to-replace inputs. This sounds diversified. In one sense, it is. Different countries do different jobs. In another sense, it is fragile. If one link fails, the others cannot simply fill in. A logic chip without HBM is limited. A design without EDA tools stays on a screen. A fab without specialty chemicals stops. That is how efficiency turned into dependence. Not through one monopoly, but through several tight bottlenecks connected together. Washington made the shift official in 2022. In August, President Biden signed the CHIPS and Science Act, setting aside roughly $53 billion for semiconductor manufacturing, research, and workforce training. That alone was a big change. For decades, the US had talked about markets and efficiency. Now it was openly using industrial policy to pull chip production back toward home and trusted partners. Then, in October 2022, the US tightened export controls on advanced chips, semiconductor equipment, and design tools tied to high-end computing. The goal was not vague. It was to make it harder for China to access frontier capabilities with military and AI value. The law also came with guardrails. Companies taking CHIPS money faced limits on expanding advanced capacity in countries of concern, especially China. So chips stopped being treated like ordinary trade goods. They became strategic infrastructure, managed with subsidies, rules, and denial. If TSMC shows how manufacturing concentrated, ASML shows how one tool became a gate. In Veldhoven, ASML builds EUV lithography machines, the systems used to print extremely small features on frontier chips. EUV works at about 13.5 nanometers and depends on mirrors, vacuum chambers, light sources, masks, software, and precision engineering that few industries on Earth can match. That is why replacing ASML is not like ordering from a backup supplier. A rival would need to recreate a whole ecosystem of optics, metrology, process control, and industrial know-how. And the power is not only technical, it is political. Dutch export licenses help decide who can buy these machines. That gives the Netherlands unusual leverage. A permit signed in The Hague can affect AI hardware plans, military chip access, and the pace of industrial catch-up in another country. Still, there is a fair question here. If the gate is so narrow, how did anyone get around it at all? The answer came in 2023, and it surprised a lot of people. Huawei released the Mate 60 Pro. Analysts linked its Kirin 9000S processor to SMIC and to 7-nanometer class production in China. The striking part was not just the chip, it was the method. China did it without EUV. Instead, SMIC appears to have relied on older DUV immersion tools and multi-patterning, repeating lithography steps to reach smaller features. It is a workaround, not a clean substitute. More passes mean more time, more cost, more chances for defects, and lower efficiency at scale. So this is the genuine complication in the story. Export controls and equipment denial are powerful, but they are not magical. They can delay progress, raise costs, and limit volume. They do not automatically stop technological catch-up. That makes the chip struggle harder to judge. Control exists, so does adaptation. So what is the verdict? Chips are a form of hard power, but not because one country controls everything. The power comes from choke points that are hard to replace quickly. Taiwan matters for advanced logic. The Netherlands matters for EUV lithography. The United States matters for EDA software, chip IP, and export controls. South Korea matters for HBM and memory. Japan matters for specialty materials. And by 2030, advanced packaging may be just as critical as any wafer fab. The counterpoint matters too. China's progress through Huawei and SMIC shows that denial can be resisted. Catch-up is slower and more expensive, not impossible. So the simplest rule is still the best one. When you hear a claim about chip power, do not ask who talks the loudest. Ask who controls the irreplaceable tool, factory, software, memory, packaging line, or material. That is where leverage hides. And that is where modern power is now being built.